Hi, everyone. Welcome. It's my great pleasure to introduce to you Professor Kevin Q. Walsh, who is Associate Teaching Professor at University of Notre Dame and Principal at Frost Engineering and Consulting. His primary research areas are sustainable and resilient infrastructure, polluted FRP, structural framing, inventory and seismic assessment of masonry and concrete buildings, among other topics. He's a registered PE/SE in 18 states, and he has more than a decade of work experience in the structural engineering industry. He completed his PhD in civil engineering from the University of Auckland in New Zealand, and Dr. Walsh is on subcommittees for various ASCE and ACMA standards. Thank you, Dr. Walsh, for doing this. And the topic is going to be seismic risk assessment and intervention prioritization for Italian medieval churches. Thank you.
Thank you, and thank you guys for hosting me here today. This is a really cool project to get to talk about. More recently, I've been working on pultruded FRP, but my relationship with researchers and faculty at the University of Miami is generally through that research field. And I understand you guys have probably already seen a handful of presentations on it. So Pranoy asked me to talk about something a little bit different today. And this is a very unique research scope, particularly for us here at the University of Notre Dame. A few years ago, we had an endowed institute called the Fitzgerald Institute for Real Estate, and they have a number of initiatives, but one of the most significant is their Church Properties Initiative. For anyone who's not familiar with the University of Notre Dame, it's a Catholic university founded in 1842 by the Brothers of the Holy Cross. And there's a very big incentive here to support the Catholic Church with their real estate investment strategies, basically. The church itself is one of, if not the largest non-governmental landowner on planet Earth. And in a lot of countries in particular, parts of the United States, my hometown of Cincinnati in particular, and in parts of Italy, which is what we're going to spend most of the time talking about, there are a number of properties that are very old, perhaps underutilized, perhaps under-resourced, and how do you actually go about maintaining these properties or deciding how they should be used in the future? And so there's a lot of components to this, but the Fitzgerald Institute for Real Estate was one of the funding agencies on this project, as the project aligned quite well with their interests. So here are a number of medieval churches scattered across Italy. Very beautiful country for anybody who's never been there, and lots of beautiful churches. Whole lot of people involved in this project, and I'm not going to go through and name all their names. I will draw particular attention on this first slide to my colleagues at the bottom there who are in Italy and from there, who hosted us and arranged our meetings at a bunch of churches. Would not have been able to pull this off without them. And of particular importance is David Pirchio, my former master's and PhD student, and now one of my colleagues at Frost Engineering and Consulting. And he is on the call today, and I'm sure would be happy to answer any questions at the end. This was really his project, and I'm just taking credit for it here. So why are we looking at churches? Well, a lot of churches in Italy, which is a region of highest seismicity, have been seriously damaged in earthquakes, and the results are catastrophic in a number of ways. Not only do you kill and hurt people, but you lose a lot of functionality and built heritage. So how do you go about, fixing this, retrofitting the churches? Well, there are a whole lot of churches in Italy. We joke that if you spun yourself around 3 times blindfolded and just stumbled a couple hundred meters, you probably walk into a Catholic church in towns in Italy. So there's a whole lot of churches, and you can't simply say, well, let's go retrofit all of them right now. And, which ones do you start with? How do you retrofit them? There's a lot of decisions that have to be made before you just go about doing that, because certain types of seismic retrofit can be very time demanding, expensive, and of course, hurt the fabric of the church itself. So here's a number of facades as well. You can see that there's quite a bit of variety, even though we're going to talk about how we tried to make our sample population as homogeneous as possible. So we selected 72 churches across Italy. To the extent of our knowledge, this is the most geographically extensive review of medieval churches in Italy. There have been very good and detailed and precise evaluations of churches in specific regions, typically following earthquakes. But we're not aware of one that went as far north and as far south as Italy. Italy is a very parochial country, and one of my colleagues joked that the only reason I could work in both the north and south was because I wasn't Italian. So how do we go about selecting churches? There are thousands, tens of thousands of churches in Italy. So How do we select the 72 that we ended up working on? Well, there were 4 criteria, and I won't name them off. I will not name them off here because we're going to go through it here. So first is architectural and spiritual value. There needs to be some people going into the church. Does not need to be a lot. And I want to emphasize we weren't necessarily looking at large churches. You know, some of you may be familiar with St. Peter's. Much smarter people and better resource people than me have put a lot of effort into that church. We're largely focusing on smaller churches, rural churches, community churches, ones that maybe have been overlooked by researchers and certainly by investors in the past, but we still want to make sure that they are being utilized. So that by members of the community in particular. Geographic region, we wanted a spread, and we wanted a spread for a few reasons. We wanted to look at churches with some differences in their makeup, and I'll show you what some of the material differences look like, but you get very different material differences in the north versus the south in particular. And then we also have a range of seismicity. While all of Italy is by US standards, medium to high-ish seismic, there is still a spectrum across the country, and we wanted to get that diversity of seismicity as one of the components for our holistic risk assessment. So overall, our churches covered 5 ecclesiastical regions, corresponding to 6 political regions, 9 dioceses, and you can see again, we went all the way up in the north in the mountains, all the way down south to Naples. Construction period was medieval, largely between the 11th and 15th centuries. We did give ourselves a 50-year buffer on either side. And again, we're just trying to increase the homogeneity. Lots of churches built after that time period, and even some churches built before that time period. But we wanted to focus on this era as a popular church era for a lot of, again, these community churches, as well as representing an extremely important heritage value to the people of Italy. For those of you who have not been to Italy before, the layout of a lot of towns, particularly old towns, and when I say old, I don't mean American, like 80 to 100 years, I mean 1,000 years old, are quite different than we would see here in North America. A lot of these churches are not separate buildings from all the buildings around them. One of my colleagues took me to his mother's hometown, and it was literally just one building. It had tunnels and doorways carved through it, but the whole town of a few hundred people just really lived in one contiguous structure. And that's a very different structural engineering approach towards analyzing that. So we did try to help ourselves by looking only at planimetrically isolated churches. So if you look at the right there, the church needs to be standing by itself and not necessarily connected to a large number of other buildings in the community. That way we can carry out the structural vulnerability analysis that we need to more readily. So we actually did 3 phases of this work, and I'm going to focus on 2 of them today. So firstly, how do we come up with a provisional seismic risk assessment? And the goal here is to tell the facility managers of an archdiocese, how do we prioritize the churches that we should investigate further, which is going to cost more money, hiring a competent engineer, and potentially retrofit. Where are you most likely to get your proverbial bang for the buck? And if you have ever read this excellent document from the World Bank, it defines 4 components of risk: hazard, vulnerability, exposure, and consequences. And there are different definitions of this. Some people combine 2 of the last 3 on there. But generally speaking, risk is literally the product. It's the functional product of these 4 components. And we wanted to identify factors related to the churches that would represent these 4 components in some fashion or the other. And we came up with 13. So hazard, for example, would include seismicity, and we wanted to look at a number of different average return periods. Vulnerability would involve the material and the structural strength or lack thereof in different components of the building. Then you have consequences, and which would involve economics and what is lost if the church is damaged, and exposure. Who's using the church? How many people are in the church? Basically, how much life is at stake if the church were to collapse while there was a congregation in there. So we have 13 different subcomponents here that we looked at over the course of the study. And I'll start with our index of hazard. So here we looked at the peak ground acceleration, just following the Italian standard for this. And what you can see in our histograms there are combinations of basically the frequency of our 72 churches where they fell on seismicity in the country. And despite the fact we've got some pretty big gaps in the middle, we decided that these distributions fit a normally distributed curve pretty well. Now, I just told you in the previous slide that we need to combine 13 different disparate pieces of information. They don't follow the same scale. So how do you do that? So for every index I'm going to talk about in the next several slides, you have to come up with a statistical distribution so that then you can renormalize the values, whatever the values are, it doesn't really matter what the unit is, into an index between 0 and 1. And we generally use our distribution cutoffs of 5th percentile and 95th percentile in order to do that. And I'm not going to repeat this step on every slide because it would become a little bit redundant, but we use this approach on all of the indices that I'm about to cover here. And for every each of our 4 sort of major components of risk, we came up with an index of hazard. And you can see that when you take the seismicity of our 4 different return periods across all the churches in our different regions, you get a pretty good spread there between about 0.1 and 1, again, on a normalized unitless index. So the next major component of risk is vulnerability. And we wanted to look at the lack of structural strength in a building. Now, if you think about maybe major earthquake collapses that you've seen from videos of Northridge or the 1985 earthquake in Mexico City, you see buildings that get very damaged and then they tend to collapse into their footprint. That's your standard moment resisting frame building in a downtown area in, say, North America. But if you're looking at an unreinforced masonry building, particularly one with very tall and slender elements like a church, that's not always how the buildings fail or collapse. They tend to have large components that just fall outward, for example. And so what the Italians have done is identified these as macro blocks. If you look at a church, you basically pretend that it's made up of a bunch of loosely fit together, which is largely what it is, big pieces of walls. And how do those elements actually collapse or fracture or crack or fail in some sort of meaningful way? And so you can see 9 of the mechanisms illustrated in the top right-hand corner. And I just found some pictures from the internet in the bottom there to give you guys some depiction of how churches in Italy have been damaged in the past. Now, I mentioned before that there's a wide range of materials depending on where you are in the country. And I'm not going to get too much into our material assessment. There's a whole other paper and presentation on that. But I did want to give you a sense of, we have everything from sort of nicely put together field rubble to almost manufactured level of, I guess it is manufactured level of consistency of rectangular bricks and blocks. So a wide range there. And we carried out non-destructive testing. Why did we do this? Well, some of the macro blocks can only be solved if you have a sense of the material properties. And I, again, won't spend too much time on this, but we did use a Schmidt hammer and a pulse velocity test. Obviously, the owners of these churches didn't want us taking out large chunks of their building and doing destructive lab testing, as informative as that might have been. And we had a group of undergraduates who went to us. We're a very teaching-focused university at the University of Notre Dame, and we love getting our undergraduate students into the field, and particularly if they can go abroad, they're quite excited about that. So David led a troop of undergraduate students in civil engineering to Italy to help him carry out these seismic risk assessments, and you can see them lining up the grid and carry out the non-destructive material testing. So our next index is exposure. So basically, who uses the church? And we looked at a number of different flavors of this. So on average, how many people are in the church? And then a lot of Catholics nowadays tend to be, Christmas and Easter Catholics is what we call them. So you get very large congregations on major Catholic holidays, but not necessarily every single Sunday. So you want to look at both the average and the maximum occupancy here. And then the other component we wanted to examine was community utilization. Let's say that you have a small community, but they actually have multiple churches. Now, people tend to be very devoted to going to one church over another, and that's perfectly fine. But if your concern is, well, if one church collapses, but we still have another, and it's twice as big as it needs to be for the population of the city, people at least still have a church that they can go to on Sundays for holidays. So there's still a church serving its function in the local community. So we wanted to look at basically the community utilization of churches by considering the number of churches and the population of the community as well. And you can see that we came up with some log normal distributions there, which are not uncommon at all when you do anything in a sociological sector. And then finally is the index of consequences. And this is where I get really nervous. I'm a structural engineer by trade. I'm a very good structural engineer. I am not an art historian. But if you appreciate and value the susceptible heritage that is inside these churches, you need to account for it in some fashion. And so following, educated judgment, but as well as archives of the diocese and guides on basically touring guides of Italy. There's a famous guy called the Guida Rossa, and I'm pretty sure I butchered that. David's probably giggling at my attempt at speaking Italian. We had a sense of where important art was in churches. And then, of course, we also visited the churches ourselves. There was one small rural church that had an original Michelangelo statue. Incredible, right? The type of thing that you would typically see in the most famous museums in the world, sitting in a rural church. If that church collapses and there's nobody in it, that's great that nobody died, but you're still going to lose an original Michelangelo statue, and you want to account for that in some fashion. And so we have basically a heritage fabric scorecard that you see there, where we wanted to account for the importance of the art and the frescoes and the statues and the fabric in these churches. Again, very uncomfortable for me to do that. I have every bit of certainty that art historians would criticize the heck out of this approach, but we wanted to make sure it was accounted for. Otherwise, we'd have to ignore it, and we didn't feel right about that either. And here's just some examples of some of the beautiful things we saw in these churches. Just incredible craftsmanship that would be very difficult to replicate today. So it's not like you could even put a number to a lot of this art and say, well, we replace it if it were damaged. It would be very difficult to do so. But speaking of economics, we did want to know, well, what is the real estate value of this? And so we hypothesized that these churches could basically be equated to a 3-story residential building. And we looked at the cost per square meter of reconstruction. And, it seemed quite reasonable based on what we were able to procure from local contacts that you could build a functional, perhaps not quite as beautiful as these medieval churches, but a functional and nice 300-seat church for a couple million euros. And we scaled our numbers to that, keeping in mind that just like here in the United States, there is a range of real estate values across the country of Italy. Some places have cheaper real estate than others, and we wanted to account for that equivalent economic value in some sense. So you can see, again, a log normal distribution that we came up with for the multiple economic criteria. So now we have 13 different indices, subcomponents of risk, and how do we combine them all? Well, we're going to use something called the fuzzy set theory. And I'm not going to pretend to be an expert on the fuzzy set theory at all. My colleague David did the deep dive into this. I'm going to sort of struggle through the next few slides. And if anybody has any questions about it, I'm sure we'd be happy to take your questions, your more precise questions about it at the end. But basically, the process is this. We have 13 different subcomponents. You're going to take a pair of subcomponents and you're going to find a way to combine them. That gives you a new index. Now you're going to combine that index with another index that you derive from another pair, and now you're down to even one fewer index. And you just keep going through this process until you only have one index at the very end, and that's going to be our complete seismic risk index that we're going to use to have captured all of these different components and factors related to risks in the church. And here's how we set up our fuzzy set theory to do it. Now, the great thing about the fuzzy set theory is that it not only allows you to combine disparate factors or indices like you've just seen here, but you can also adjust it to account for your level of uncertainty, as well as the lack of complete independency between indices. And I won't get too much into the weeds here, but pretty much for every index that we have, you lay it down on this template that you've set up, and you create a 5-tuplet array. Now, if, for example, this was what we're showing here, and I actually don't know this, but if this were our seismic hazard and our seismic hazard was relatively low here, we'd have a 5-tuple array where we had 2 values. Again, we want to account for uncertainty. So we don't just want one value, but we want a couple of values, a range of values, sort of on the lower end. And if this were one of our churches that had a very high seismic index, then that red vertical line you'd see there would be on the right side of the sheet, and we'd have values other than zero sort of on the right side of our array. And then you have to set up an algorithm for, well, how do you combine these? How do you combine values that are very low and very low, or very low and medium? And so you basically just set up a policy for doing this. And after you process all these values, you end up with a single risk rating. Now, this could seem a bit strange to a lot of people. How do we combine all of these disparate values with a high level of uncertainty and come up with a single value? Well, you really should pretend that there's whiskers on these, and perhaps very large range whiskers. But the goal here is not necessarily to be precise. Keep in mind that our goal is to advise the facility managers of these parishes and dioceses, as well as the bishops overseeing all the properties in Italy. How do you pick one church out of a dozen to start with as your highest risk church? And the one that we've circled there was the highest risk church in the region of Lazio. What's interesting about that is, independently, through their own process that had nothing to do with what we were doing, the diocese there decided that of their several churches, that was the church that was posed the highest overall risk to them as well. And so sort of independently, we were able to validate this process, at least for one case study. By the way, whenever I talk about statistics in class, I always find some meme just to get students to laugh a little bit, because otherwise statistics can be quite dry. So I'll let you read this. I'll just presume that there is infinite laughter on the other side of this muted Zoom call. Okay, so now that we have picked one church in the region of Lazio to focus on, what do we do next? Well, here's that church, the church I circled in the red before. And again, independently, the diocese decided this was the church they wanted to focus on as well. This is the Church of Santa Maria Maggiore. And last we spoke to them, they were currently designing it for a retrofit. So at this church and several others, we took drones and pairs of cameras out, and we took full photogrammetric surveys. So we took enough high density photographs that overlaid with one another that we were able to come up with high density point clouds. And we were able to do an average church. Keep in mind that these are 300-person churches, not the size of a St. Peter's, in about half a day. So say 3 or 4 hours or so. And here's what some of the images representing sort of the lower resolution point clouds look like. So from both inside the church, where we use stationary cameras, and outside the church, where we use the drone. For obvious reasons, we were a little afraid of using a drone inside a church for fear that we would hit something. And here are some higher density images of the Santa Maria Maggiore. Again, these are not photographs. These are developed from the point clouds. And on the left is the exterior. And then on the right is the interior, kind of seen from the outside, so that it makes a bit more sense as to what it is. So we've got a full surface model of both the exterior and interior of the church now. And we had some fun with it too, did some flyovers. I was afraid to run a video on today's Zoom call, but here's our students up in a tower of one of the churches with some mountains in the background. So it's pretty cool having a drone out there with you in Italy. So once we had this point cloud, we were able to put this into a BIM-based three-dimensional model, such as Revit, for example. And again, the beauty of having it in a software like that is you can cut it however you want, look at any part of it. But perhaps the even biggest benefit of having it in a comprehensive BIM platform is, what do you do with all this information? We've captured all of these risk components of the churches. We've taken pictures. We found very few documents. None of these medieval churches have documents, but maybe there's something that was relevant to the church that we have here. We have non-destructive testing material data from, our Schmidt hammer test, for example, and our pulse velocity. Where do we put all of this? And so a common trend in the construction industry here in the US for higher end buildings, as well as it should be everywhere, in my opinion, is to make sure that we're capturing all this facilities asset management data in one place so that we can use it for the future. Why am I going to need my materials strength values tomorrow? I probably won't, but there's a darn good reason why I might need them 20 years from now. So you've got to put all this information in one place. And I'm really excited about the trend we've been hearing that it's coming for 20, 30 years, but we're finally starting to see it in the AEC industry, about putting all this information in BIM, not just for the initial construction, but for long-term facilities asset management. And that's what we were able to provide to several of the dioceses, BIM files with all this information stored in one place. So now that we have it in a BIM platform like Revit, you can now export it into a structural analysis software. We use SAP 2000. And first thing we did was carry out a modal analysis just to understand the dynamic behavior. And primarily, we wanted to identify which macro blocks, if you think back to that earlier slide, are most likely to be affected. It's probably not shocking to most of you that if you have a very tall, slender bell tower, that's a very vulnerable macro block to dynamic shaking. We also carried out a response spectrum analysis to identify where the highest stress distributions were in any given building. And then we used all this information to make our best judgment as to where the local failure, collapse, or cracking or fracture mechanisms would be. And then there's a number of generally simple hand calcs that you can carry out to identify that. So here you see basically the keystone in a rose window that we identified on this particular church as being a potentially very vulnerable element because it's sort of a tall, slender parapet there and there's not a lot bracing it. And so we can carry out a hand calculation to determine, hey, what is the likelihood that this is going to collapse in a given return period earthquake? And if it's likely, then that is the element that that they should retrofit with a prioritization. So what we've done here is started very macro scale. We've worked ourselves down to very micro scale. We've identified the church in a given region that poses the largest overall risk. And we want to break that down too, in case the diocese has any questions. Well, why is it the overall risk? So there's a lot of nuanced questions to be asked and answered there. But we've gone all the way down to, hey, if you only have a very limited amount of money to spend on this church, here's the thing you should probably retrofit as a priority. Just wanted to acknowledge David again, who did a ton of hard work on this and really not only created a great thing for himself and communities in Italy, but also launched a very exciting career for a number of the students who went with him, who went on to graduate school to do research themselves and pursue wonderful careers in our industry. So thank you to David for that. If you want a lot of detailed information on this, we've published 3 papers, which, by the way, is a heck of a lot of papers for a master's thesis. So well done, David. I understand that this presentation is being recorded, so you can come back and find these later if you needed to. And for anybody who wants to follow up with any questions on this research, I have my email address at Notre Dame down there, as well as David's at Frost Engineering, and we'd be happy to answer any questions.